Okay, good evening everyone. So just wanted to record this short video regarding this project. So this is the closest pair of points algorithm that was studied in class. There's two main approaches to this algorithm in particular. So you have the brute force implementation and the divide and conquer implementation. So first just want to go over just the setup, the different data structures. So there was just one data structure in particular for this problem, which is just the point. So the points is just made up of an x-coordinate and a y-coordinate. I have a distance method to measure the distance between 2 points. And I have two methods that'll take care of printing or pre-printing the points when I want to represent the point in a string or in a print statement. I have also defined two functions that'll just tell me if the point 1 is the same as another point 2, which we're going to see in a minute, and the get closest pair of points for brute force. So this is the brute force implementation. It seems pretty simple. You just do a double for loop in both arrays. In the point array. So remember that for this specific problem, what we pass in is an array of points, and what we get back is the pair of points that is closest to each other. So going over the implementation very quickly, here I have a timer, which will tell me the time, how long the algorithm took to execute. And here I'm just doing a double for loop for every point in the array. I'm just checking the distance between that point and every other point in the array, no matter how big that is. So the runtime for that specific implementation, for the brute force implementation, is going to be big O of n squared, just because of the double for loop. So I'm returning the closest pair, the closest distance, and the time it took to execute. In regards to setting up the data, so I worked with powers of 3, so I have 10 arrays, 10 lists. So each of them are a value of n from 10 to the third power all the way up to 10 to the fourth power. We are basically using the randint function in the random library to get random sets of points, which I did print out here. I only did print out around 20 out of all like 1,000 to 10,000, and that is because sometimes Collab does not like to print out so much and you get a warning. So I figured I would at least show you guys that the points are unique, and there are a lot of them depending on how you seed the data. You might get a double point, but I tried to get rid of those in the trials. So regarding trials, there's m trials. M is 5 in this case. So here are the runs for the brute force, and I made 5 trial runs, which is what this for loop is all about. So pretty much just consistent. It gives you the time it took and the number of runs. So we're doing that all the way until I'm done with 10 to the fourth. So here I'm just applying the average runtime versus n. Seems pretty consistent. I'm also going to graph the empirical versus the predicted runtime, which is also very consistent. So that tells us that our empirical runtime just about matches our predicted runtime. It's very close. Divide and conquer approach, a little different. So basically this is going to use that algorithm that we discussed in class. We're going to grab all the points, split them in half using a line L. And then we're going to create a box with, I think, 16 little boxes. Each little box has a point, or at most 1 point, my bad. And we're just going to find the closest pair of points on the left side, on the right side, and another pair of points S. S0 is on the left side, and the other point S1 could be on the right side. So that's where this comes in. And same thing as before, we have 5 trial runs per value of n, same values of n. So I got some very strange results, which I was trying to debug before, and same for the other one, which works. Again, the results were a little strange, but it seems like with lower values of n, the algorithm seems to work just fine, but for some reason as you keep increasing it, it starts to behave a little strangely, but hopefully the trend is understood. So here, same weird situation for the empirical versus the predicted runtime. Seems like it's kind of straight at first, and then loops around and then becomes straight again. But just like the before algorithm, it should be straight. Also plot the empirical versus empirical runtime for brute force and divide and conquer. And last but not least, I also want to go over just a simple test case here. Just ran it through a pair of 10 points, then a pair of 3 points, and got the same results. And that's it. Thank you very much, everyone. Have a good day.